And dimensional analysis is all about having units that agree when you do mathematical operations with them. So for example, in this sign, here we have a sign that claims that in New Koyama there are 562 people. The town is 2,150 feet above sea level, and it was established in 1951. You add those numbers together and you get 4,663. What does this number mean? It means absolutely nothing, because these numbers all have different units. They're all very different kinds of things, and adding them together just doesn't make any sense. And this is what dimensional analysis is all about. It's handy for equation checking and allows us to see if an equation makes sense. So if you have an equation, the units on one side of the equation should match the units on the other side of the equation. In addition, if you have multiple terms that are added together, those terms should have the same units. So you can plug in what the units are for different variables and then check to make sure that the units do in fact match. So if we use this equation as an example, we have a distance, which is a length, is equal to 1/2 acceleration, which happens to be a length over a time squared. We'll learn more about that later, times time squared. So the time squareds would cancel, and we have length on one side and length on the other side of the equation. Now over here we have an equation that suggests that distance is equal to velocity over time. Distance has units of length. Velocity has units of length over time, like miles per hour, and time has units of time. And so if we simplify this equation, we get length over time squared, and that's equal to length. No, the units don't seem to match at all. And so this equation is definitely incorrect. Now, over here, the dimensional analysis checked out, but we didn't use the fact that there was this 1/2. So dimensional analysis can tell us if an equation is definitely wrong, but it can't necessarily tell us that an equation is correct because it doesn't give us a way for checking these constant factors. So let's try that out. We want to know which of the following could possibly be correct. So in equation A, we have velocity is equal to an initial velocity. That's what the sub-zero means, that this is an initial velocity, plus an acceleration times time squared. Here we have a volume is equal to an area times a height, and the last equation says that a mass times an acceleration is equal to velocity squared. Which one of these could be correct? And I have, as a hint, I have the SI units for all of these various quantities.